Hey, welcome back. This is now 10.5. Hopefully I won't have another coughing fit on you. But anyways, we're going to be working with integration here. So this is kind of a nifty thing, doing integrals in polar coordinates. But anyways, there's also arc length again. There we go. So here we go. So before, recall the work with the Riemann sum and the Riemann man. So or the Riemann person, in order to find the area under the curve, what we did was section it up into a bunch of little rectangles. And then, this rectangle, presuming the function is called f of x, the area of that rectangle is, this is located at position x sub I, and its width is change in x. The area is going to be the height of it times the base of it. So the height would be f of x sub I, and then the base would be change in x, right? And then Riemann person runs across, adding up all of those areas. Then we're going to help them out by taking the limit as the number of those rectangles goes to infinity, and then we end up with our integral. Okay. So we kind of want to do the same thing with polar curves, but it'll be a little bit different. We'll need a different kind of geometric object to get the job done. And that geometric object is going to be the sector of a circle. So instead of rectangle, we use the sector of a circle. And the formula for the sector of a circle, you actually do know it, believe it or not. If you know pi r squared, you know this, because that formula is based off of this formula. So the formula for the sector of a circle, which is the area in particular of the sector of a circle, just kind of think of it as like the area of a piece of pizza. The area would be 1/2 theta r squared. So note, there I go, yeah. Then theta is equal to 2 pi, you get the area of a circle. Okay, so we use that idea, and now Riemann person is not running across the x-axis. Riemann person is actually going to be going in a circle. So let's take a look at what we got here. We'll have some, polar curve, maybe starting at theta equals alpha, and then rotating over to theta equals beta, and at the same time tracing out whatever, maybe some sort of weird blobby thing like this. What we'll do is section it off into a bunch of sectors of circles. So instead of rectangles, you have these things. We'll go after the formula for this particular guy right here. And we could call this person a sub I. This time, the position of a sub I is going to be given by theta sub I. Okay, so this, you can maybe put in an angle line here. Say that position is theta sub I. And then instead of change in x, what you have is change in theta. So above it, let me put in get another color, change in theta for the sort of width of the angle. Okay, so a sub I is going to be 1/2 times theta sub I, and then, well, change in theta sub I guess, is rather what we really want. We need the r squared thing. So what is the r squared? Well, we didn't really give this curve a name, so let's call the curve r of theta. Instead of f of x, we call it r of theta. It's that curve. I'm continuing it a little bit. You know, whatever it does. So it's kind of trying to smush all this in blue. We have the r of the position is theta sub I, and then times the change in theta, which would be kind of this angle right here in the picture of the circle above. Okay, so times change in theta. And that becomes kind of the thing that the Riemann person is going to be adding up as they, in this case, rotate around the pole. Okay, so you're not running around an axis now. Riemann person is going in circles. Adding up all these little sectors. And note, Riemann person, you don't want that person to over add. So you remember in 10.4, I was kind of, you know, this curve is traced out going from here to here. That becomes important. That's why we need to do it by hand, because the calculator isn't really going to tell you. I mean, you could watch the calculator graph it and try to guess, but if you're doing that, I don't want you building my bridge, okay? Want somebody guessing it, you know? Trying to risk my life for going to work every day because somebody wanted to guess the answer. No. Okay, so anyways, Riemann person is adding up all these values. So it's a sum of all these 1/2, and I really should have squared this expression. So 1/2 r of theta sub I squared times change in theta, and then we are limiting this, making those wedges as small as possible, and then this will turn into our integral du jour, the integral from alpha to beta of r of theta. Instead of using r, they're going to write f of theta squared and then d theta. Okay. Okay. So if nothing else, this is the formula we need for figuring out area, and we need to know the starting place and the end place in order to get the appropriate area. So let's take a look. Number 4, find the area of 2 petals of the rose curve. Okay, so like I said, we need to graph the thing. There's no, as far as I can tell, there's not going to be any easy way. I kind of have to maybe develop a different way to introduce the material, but to find the 2 petals, you really need the alpha and the beta, right? There's no way to get it except to do this by hand. So I'm going to go through my usual process. The amplitude here is 4. The period, you take this 3 theta and wedge it in between 0 and 2 pi. Divide by 3. And then section it off into 4 parts for the tick marks. Okay, so let me graph it in the r theta plane. Just in case I need more tick marks. Oops. I don't know why. And it's going up to 4. Sine starts at 0. And there we go. All right. Go to our theta plane, and I need to figure out how long it takes for me to get 2 petals. Okay, so we need 4 circles. I'm going to put my angle lines in red. Pi over 6, 2 pi over 6, 3 pi over 6, 5 pi over 6. Okay, and then I'll do my curve in blue. So from 0 to pi over 6 here, it'll go from 0 to 4. So it's increasing from 0 all the way out to 4. And then from pi over 6 to 2 pi over 6, it'll decrease back to 0. 2 pi over 6, it decreases back to 0. And then from 2 pi over 6 to 3 pi over 6, now it's going to go negative. So 2 pi over 6 to 3 pi over 6 is this sector, but really we're on the negative side down here. Okay, so it's going to increase to -4 in that region. And then from 3 to 4, this sector, and of course we're still negative, so it's actually in this sector, it's going to go like this. And then we got it. We got our 2 petals. So 2 petals from 0 to 4 pi over 6, which is 2 pi over 3. Okay. You don't really need to even go that far. You can just draw 1 petal and then double the area, because these things have supersymmetry, right? It's not going to be like one petal is a different shape than the other petal. It don't work like that for us. Okay. So they're all the petals are going to be symmetric. So if you wish, you can integrate going from 0 to 2 pi over 3 of the r function squared, so 16 sine squared 3 theta d theta, but that will be the same as going 2 times the area of 1 petal. And we got the area of 1 petal just by going from 0 to pi over 3. It just depends on what you feel like doing. If you do the second one, it's a little easier because you really only have to trace out 1 petal and then go from there, right? But anyways, let's just work with the second expression. So 2 times a half is 1. Then we have a factor of 16. We can pull out of the integral. And we end up with a trig integral. And to pull these trig integrals off, you're going to need to have memorized those half-angle formulas. I think they're power reduction formulas. So basically, sine squared of theta, you have to rewrite it as 1 minus cosine 2 theta, so you double the angle. Or you're going to have a cosine squared theta, so you'll rewrite that as 1 plus cosine 2 theta over 2. You need those memorized, peoples. Okay. So in our case, we have the sine version, so it'll be 1 minus cosine, and you double whatever angle is sitting there. That angle is 3 theta, so you'll get 6 theta out over 2 d theta. And then we're going to butterfly it, so I have 16. You can factor out the 1/2. Let's just do that. And then you have 1 minus cosine of 6 theta d theta. 16's halves is 8. The integral of 1 is theta. Integral of cosine is sine. If you do a u sub, you'll get a factor of 1/6. And then we want to go from 0 to pi over 3. This will be 8 times pi over 3 minus sine of 6 times pi over 3, which is the same as 2 pi. Sine of 2 pi is 0. And then minus plugging in 0, you get 0. Sine of 0 is 0. So we're just going to get 8 pi over 3. So fairly simple. For the quiz today, try to find the area of 1 petal. And of the same curve. Okay, so 4 sine 3 theta. So I mark that down. Okay, and just some remarks on the test. You will have to show this work where you're, so on the quiz as well, please show your pedal work. So I would need to see what I would need to see. So if you're doing anything less, it's kind of like, well, this person used a calculator, right? I mean, that's it. I mean, there's no other way you could have done it without, you would have to use a calculator. So you're basically, if you don't want to show the work, you're telling me you're using a calculator, which I'm saying you're not allowed to. Okay, you're not allowed to use a calculator to graph these things on a test. Okay, so that's been said. Anyways, please show me, you're going to have to do the amp, the period, the ticks, the r theta plane graph. So here is my theta axis, here's my r axis. Then you have to do it in the polar coordinate system. And then you have to do your integral. I mean, there's just simply no other way of doing it. Sad to say, it's sad to say, it's just, that's the way it is. And if you try to pull one off like, oh, I found some, no, there's no other way to do it. It's either this or you're telling me that you don't know enough about what we're doing in order to know that what you're showing me is not enough. So there's our last video quiz. Just find the area of one pedal. Again, please show me the r theta plane, show me the polar curve. You don't have to do the whole curve, you just show me one pedal. Tell me how long it took you to graph it, so from 0 to what angle, and then you should do your integral. Please show all the bits, all the bells and whistles. Okay, moving on. So get number 5. So r equals cosine of 7 theta, and we want one pedal. Nasty 7 inside the cosine, but it's not a big deal. First, the amplitude is 1. Second, then the period is kind of weird. So we got 7 theta in between 2 pi and 0. Divide everything by 7. And then get your tick marks. So you're dividing that by 4. And so these are by pi over 4, 14s. Six, 7, 8, 9, 10, 11, 12. And it seems like it just keep on going on and on and on. But we'll see what that gets us. Okay. Cosine looks like handlebars of a motorcycle. This. And then we're going to go to our xy plane to graph it on the polar coordinate system. So it looks like we just have one circle we need. Okay, so how the heck am I going to graph these pi over 14s? Well, think and so we have crap. We're starting at 0 and then we're going to pi over 2, right? What is pi over 2 if the denominator was 14? So you're just going to have to multiply top and bottom by 7. So what does that tell me? It tells me that we're going to section off that sector, that first quadrant, into 7 parts, right? So it's going to be 1, 2, 3, 4, 5, 6, and then 7 pi over 14 will be your pi over 2. Okay, so those will be our angles. 1, 2. If you need to go into the third quadrant, you can extend those then. But hopefully we just need one pedal or something, so we won't have to go crazy with it. Right. So what is it? Yeah, it's one pedal. So I'm starting at 1 when the angle is 0, and then going from 0 to pi over 14, it's going from 1 to 0. So as it rotates, it'll turn into this curvy part of the pedal, and that'll be half the pedal. So because these things are supersymmetric, we can just multiply our integral by 2, right? So we can go 2 times the integral from 0 to pi over 14. there's automatically a 1/2 in front. I just forgot about that. But then on the inside, it'll be cosine squared of 7 theta, d theta. Okay. So the area of 1/2 the petal would be this integral. We want 1 full petal, so why not just multiply that by 2? And that's exactly what I did. That way I can kind of avoid having to spend all this time graphing. And here I am. Okay, so I do an integral. I'm going to have to go 1 plus cosine 14 theta all over 2 d theta. I'm going to factor out the 1/2 and then integrate the 1 plus cosine 14 theta. That will be 1/2, and then the integral of 1 is theta. The integral of cosine 14 theta is going to be sine of 14 theta all over 14. And then I have to evaluate from 0 to pi over 14, which shouldn't be too painful. You get 1/2 theta is pi over 14, plus sine of 14 times pi over 14 is just pi, right? So sine of pi is 0, and then minus plugging in 0, you get 0 for both of those. So you're just going to get pi over 8. Or sorry, pi over 28. So pi over 14. Blame the coughing. It's all the coughing. Okay. Moving on to more complicated objects, like the snails. See if I can do a better job of drawing out a snail. All right, so first the amplitude is 10. Secondly, the period is easy this time. Just going from 0 to 2 pi. So the tick marks, 2 pi over 4. So it's going by pi over 2s. Then what do we have? We have a shift up 5. Okay, so let's try to graph this thing. Going by 5s on the y-axis. Pi over 2s. I mean, it's not the y-axis, it's the r-axis in this case. Okay. So it's a cosine function, so it looks like handlebars of a motorcycle. So originally, it's this curve, right? But then there's a shift up by 5. So it's going to change kind of the center from being the theta axis to this line right here, r equals 5. And it will take the whole graph and shift it up like that. So now it's going to go through here and then bottom out at -5 here. And it's going to go through like over here, and then top out at 15. Okay. So let's take a look in the XY plane with our polar graph paper. I need to go up to 15. I'm just going to use 3 circles, each at 5 units apart. And my tick marks are just at the axes, so 0, pi over 2, 2 pi over 2, which is pi, 3 pi over 2, and then 2 pi. So I'm starting out at 15. I'll do that in purple. And then as I rotate the pi over 2, it's going to decrease to 5. Right? So it'll decrease all the way to 5. So that was this, let me put it in yellow, this portion right here. Okay. The next portion, I'll put it in blue, from pi over 2 to 2 pi over 2. In other words, from pi over 2 to pi, which is now this sector. What's happening? So at some point, it's going to hit 0. So it's decreasing, and then at some angle it's going to hit 0. And then it's going to loop into the negative sector. So it's going to, at some point, hit 0 on this positive portion, maybe like right here. And then it's going, that extends through. Then as it's going to start looping back in on itself, kind of. So, you'll get some point maybe here, and then it's going to loop all the way over to -5, like that. And that'll be at pi. Okay, so hopefully that's a little bit more clear than what I was doing last time. Probably not very much, but there it is. Okay, so the next region then is going from pi all the way up to 3 pi over 2. And again, it's going to hit 0 and then cross into the other sector, right? So it's down below at -5, and then eventually it's going to cross through the pole and then increase up to 5 at 3 pi over 2. Okay. So let me be a little bit more careful and kind of put in some angle lines so we can watch it as it goes through and around. Okay, so it's down at -5 when the angle is pi, so it's right here. And then as we rotate in this sector, it's going to first increase back up, right? So it's kind of traveling back up to here, and it'll hit 0 again. That completes the head of the snail, okay? So at this point, it's completed the head of the snail. It's in this region from here to here that the heads of the snail is being traced out. Okay. But once it hits 0, then it's going to cross back over into the positive portion of the sector and then increase back to 5 at 3 pi over 2, right there. Okay. And then finally, it'll increase all the way back out to 15, like that. Okay. But anyways, long story short, to get the inner loop, which is the head of the snail, we basically just need to find these two locations, these two theta value locations. And where are those? Those are where r is equal to 0. So note the position, it's going to be theta comma 0 in both cases. I just, theta 1, I need to figure out theta 1 and then theta 2. So how do I do that? Well, you take the original equation, 5 plus 10 cosine of theta, and set it equal to 0. Right. All right. So it'll be 10 cosine theta equals -5. That will be cosine of theta equals -1/2. So the reference angle for cosine to equal 1/2 is pi over 3. And then we are in which quadrant, right? It's second and third quadrants that we want. For theta 1 is in the second quadrant, and then theta 2 is in the third. Okay. So again, the reference angle is pi over 3. This is the reference angle, but we want the one that's in the second quadrant, which is 2 pi over 3, and then the third quadrant, which is 4 pi over 3. So those are the limits on your integral. Right, so our integral will be 1/2 integral going from 2 pi over 3 to 4 pi over 3. And unfortunately, it's kind of nasty, right? You're going to have to FOIL 5 plus 10 cosine of theta squared d theta. Okay, so this would be 1/2 integral 25 plus, looks like 100, 5 times 50 is 50, plus another 50. Cosine theta plus, really? 100 cosine squared theta. Makes me think I made some sort of arithmetic error. 5 times 5 is 25. 5 times 10, It's 50 plus another 50 is 100. 10 times 7, oh, this looks right to me. So we get 25 plus 100 cosine theta. For the third term, you need to convert that. There'll be a 1/2 fraction, so it'll be 1 plus cosine of 2 theta over 2 times 100. But you can change that in the 50 times it, right? So 50 times 1 plus cosine of 2 theta d theta. And then we want to combine some like terms. So when I distribute this, I'd get a 50 plus 50 cosine of 2 theta. And then I want to combine that 50 with that 25. So I get 1/2 integral 75 plus 100 cosine theta plus 50 cosine 2 theta d theta. And then I get 1/2 75 theta plus 100 sine theta plus, it's going to end up being, there's a u sub there, so it could be a factor of 1/2, so it'd be 25 sine 2 theta, and then evaluate this critter on the limits from 2 pi over 3 to 4 pi over 3. So it'd be 1/2 times 75 times 4 pi over 3 plus 100. 4 pi over 3, 1, 2, 3, 4, it's in the negative for sine, right? So third quadrant, so negative √3 over 2 plus 25 times 8 pi over 3, which I think is in the second quadrant there, so it'll also be negative. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So negative √3 over 2 minus 75 times 2 pi over 3 plus 100. 2 pi over 3 is in the second quadrant. Sine's positive over there, folks. Why did I do that? 8 pi, so 6, 7, 8, sine is positive in that. Okay, so then this is 2 pi over √3 over 2, and then plus 25 times 4 pi over 3, 1, 2, 3, 4, that's negative √3 over 2, I believe. Okay, so 3 goes in the 75 25 times. 25 times 4 is 100 pi for that part. And then this part, 3 goes in the 75 25 times. 25 times 2 is 50 pi. So this will be 1/2 times 100 minus 50 is 50 pi plus minus, looks like 200 √3 over 2. But that would just be 100 √3. And then we get 25 plus another 20, so 50 √3 over 2's. That would just be 25 √3's. And then this would be 1/2 times 50 pi minus 75 √3, barring any arithmetic errors. And I don't have it written down in my notes, so I'm sure I made one. But anyways, there's the idea. Okay, ultimately, in this section, the sort of, one of the sort of capstones is to be able to integrate between two curves. So recall this stuff that we did in chapter 7. We want to find the area between these two curves, right? This area here. So in order to do that, it's always bottom curve minus top curve minus bottom curve, right? Let's put in some points here. And on top of that, we need to know these intersection points because the first region from A to B, the top curve is F. And then to find the area of that second region from B to C, the top curve is actually G. So it'll be G minus F. Okay. In the new setting, well, first off, we need to work with these points of intersection. The problem with the points of intersection is this non-uniqueness thing going on. Okay, so it's kind of difficult. It'd be difficult to solve out for those points when you're working with polar equations. You won't always get the right answers. Okay, and also just trying to figure out what is on top and what is on bottom can be kind of a nightmare as well. So the problem we'll look at is more like this. So I have maybe this scenario going on where I'm maybe not really worried about the curve, the area in between, but rather the area underneath. Okay, so I want to know this area instead. Kind of looks like a crown. If you go to Burger King, you get those crowns. I don't know if they give those out anymore, but you used to be able to get a little crown with your meal. So anyways, how would I figure that out? Well, it's just in this first region from A to B, you're going to be using the g curve. So it's the integral of g of x dx from A to B. So it's basically you find the bottom curve. And then the second region from B to C, the bottom curve is f of x. Okay, so now in our work, we're going to have these polar curves. So you may have maybe like two polar curves. This is kind of a goofy one that I make up for fun. So maybe there's one curve, and then the other curve is kind of going out where the other guy's going in. Right, so we'll make the black one. This guy, call him f of theta, and call the other guy, the purple one, g of theta. So we need to find the intersection points again. And with regards to what is on top and what is on bottom, you have to imagine that now the Riemann person is running around the flagpole, so to speak, right? So with regards to the Riemann person, maybe he's sitting right here, and he's running around, the person's running around the circle like this. The bottom curve going from maybe alpha 1 to alpha 2, the bottom curve is f, right? And then maybe going from alpha 2 to alpha 3, the bottom curve is g. So for instance, if I wanted to find the area of this kind of, it looks like a star or something, maybe I'm making Chinese stars for my company or whatever it is. I'm a freelance mathematician and I have to do all this work for people. So I'm trying to figure out this region here. They want to know the area of that throwing star so they know how much metal they need to put forward. It's a terrible picture, but how would I do that? Well, you would integrate. Well, first, maybe this is angle 0 here, so I got to go from 0 to alpha 1. And in that region, it's the g curve. And then, so that would have been right from here to here. And then from here to here, it's the f curve. And hopefully you get the idea, right? It's exactly what you were kind of doing before. It's just the Riemann man now, the Riemann person is running around the pole. So with Riemann person's orientation, what is bottom and what is top may be a little bit different than what the rectangular coordinate Riemann man orientation is with respect to what is on the bottom and what is on the top, right? Okay, so that's a bit awkward, it's a bit weird. And then on top of everything else is this issue with the points of intersection that we need, these alpha 1, alpha 2 values, and it becomes a headache because of the non-uniqueness issue, okay? So anyways, points of intersection is what we want to hit first. And we'll look at number 8. So they're saying theta is pi over 4. and that's one equation. So theta is equal to pi over 4, and then r is allowed to vary over the real numbers. So what is that as a curve in our polar graphing paper here? You're fixing theta to be pi over 4, right? So that's right here, pi over 4. And then you're letting the r value vary. So the r could be 1, it could be a half, it could be 3/4, it could be 1.5, it could be anything on that line. It could be -1, -0.5. So what you end up with is a straight line through the origin, like this diagonal line. Okay, so that's our first curve. I did it in blue. The other curve they're looking for is r equals 1. And of course, that's just a circle, so I'll put that in purple and presume that this was located at 1 unit away from. Okay, so what is the intersection between those two curves? It's these 2 points right here, right? In particular, they're probably going to give you a range of values, so they want from 0 to 2 pi. Okay. So it looks like you could just kind of look at the picture. One point would be at, and it's r theta, so 1 comma pi over 4. The other point, and what you don't want to do is rotate that angle. So you may want to say, all right, I'm going to put it at 3 pi over 4, comma, but in actuality, for this intersection, the theta is pi over 4. So you have to keep that pi over 4 the same for whatever reason. And then to get it on the other side here, you just put a -1. So you're going to move by an r value of -1 instead of +1 to get to the other intersection. Okay, so that's kind of a simple one. You could visually figure it out. Let's look at a harder one and kind of kill all birds with one stone. So in this next problem, it's going to be kind of like what we were doing here. We got to, kind of figure out what's on top, what's on bottom, figure out the angles and all that jazz. Okay, and that should probably do it for this video. Oh, no, we still have to do arc length. I apologize. Arc length's no big deal. Okay, so anyways, number 9. Find the common interior. To the curves r equals 4 sine 2 theta, and then r equals 2. Right. So first, I don't even know what they are. I'm going to have to graph them out. So, I mean, the second guy clearly is just a circle with radius 2, but the first one I got to work with. Amplitude's 4. Period. Wedging 2 theta in between 2 pi and 0. Divide by 2. Tick marks. Pi over 4s. Okay. Go to my r theta plane. It's a sine curve, so it starts at 0. It should go up to 4, and then down, and then back up. Okay, so these places are 4 and -4 for the amplitude. Then we'll go to our xy plane and hopefully graph the thing. And I'm going to kind of carry on a little bit lower. So going by 2, so the inner circle is at position 2, and then out to 4 here. I need angles at pi over 4s, so I just put those angled lines in black again. Okay, so the first portion on the top here, from 0 to pi over 4, it's increasing out to 4. So my curve will increase out to 4. And then from pi over 4 to 2 pi over 4, it'll decrease back to 0. Okay? And then from 2 pi over 4 to 3 pi over 4, it's going to go negative. So 2 pi over 4 to 3 pi over 4, this sector is actually going to be drawn out in this bottom sector. Okay? So it's going to increase firstly to -4, like this. And then it's going to decrease back to 0, going from 3 pi over 4 to 4 pi over 4 in this region. Okay, so it's going to, what did I just do on the r theta graph? I went back to 0. Oh, whoops, from 2 pi over 4 to 3 pi over 4, I go back to -4, I go down to -4. And then I increase back to 0 in this sector right here, back down on the polar graph. Okay, keep going. So now I'm repeating the curve. And from, what would this be? 4 pi over 4 to 5 pi over 4, which on our polar graph below, 4 pi over 4 to 5 pi over 4 is this sector here. I'm going positive, so I'll zip out like this. And then from 5 to 6, I'm decreasing back to 0. Okay, and then from 6 to 7, it's going to go to -4. So it's actually in this sector down here. So 6 to 7, it'll go to -4. And then finally, it'll finish it off going from 7 to 8. It'll increase back to 0. Okay. So we were negative, so it's really this sector, but you know, it was drawn out in the opposite sector. Okay, so there it is. It's a 4-leaf clover. Then we could draw out the r equals 2. I'll do it in yellow. So that's this curve. And we want to know the common interior. So what is that? That's going to be this junk. So you can think of it like maybe you're trying to figure out the area of a propeller that you're going to use. In your new jet plane, or I don't know. I know they don't use propellers in jets. If that's what you're thinking, I'm not that naive. Okay, so that junk, right? All right, so we need to figure out the intersection points. That's one issue. So for example, that intersection point right there. Because so in the first region, it's the Rose curve that's kind of telling you the top for the Riemann person. And then the next part of the region up to here, it's actually the circle that's telling you the area. And then it flips back over to the rose petal being on top. Okay. So hopefully that's kind of clear. I'm going to zoom in on it, and then hopefully it will be real clear. So, but anyways, in this first region, the rose petal is basically telling you the height of those sectors of circles that you're using for the geometric figure for the area. And then in this next bigger sector, it's just the area, the circle, which is telling you basically the little pizza wedges distances. And then in the last region, it flips back over to the rose petal again. Okay, what we're going to do is just zoom in on this region from 0 to pi over 4. Because if we can get that region, all we need to do then is multiply it by 8, and we'll have our area because of the symmetry. Okay, so I'm going to zoom in on that first quadrant just from 0 to pi over 4. So the graph of the rose petal kind of went like this. Oops. And then we got another circle in there. And what I'm saying is that in this, there's going to be kind of like two sections. There's this angle right here. And in that angle, the top portion is given by the rose petal curve. Right? To figure out the area with the integral, you're using the rose petal. You're not using that red curve. It's the rose petal curve. So you think of that as kind of, if we were thinking back to the rectangular coordinate system version, that it's the bottom that we're looking at. So hopefully you can kind of tell that. The bottom curve is this curve. The top curve is the one I'm doing in yellow right there, right? Okay, so I need to know then that intersection point, and I can get the area of this little wedge just by integrating the rose petal in that region. And then I'm going to use the circle formula from this angle, whatever it is, I'll call it alpha, to pi over 4 in order to get the area of this wedge. Okay, and then I just multiply the whole thing by 8. Okay, so what I want to show you now is the getting the intersection, how to find the intersection points. And if you look at the curve as it's drawn, there should be 1, 2, 3, 4, 5, 6, 7, 8 of them. Okay, there's 8 intersection points. The way you proceed is just like what you did in algebra. To find the intersection points, you're just going to equate the equations, set them equal to each other. Okay, so you're going to say 4 sine 2 theta equals 2. Okay. There's a big problem with this. The problem is that when we graphed out the rose petal, a lot of our points were actually negative. Okay. The output points, some of these points on the curve were negative. Like I think this one and this one were -2. The trouble is that the r equals 2 formula never hits -2. And maybe in this case it could be argued that we should use for the formula r equals plus or minus 2. Because then when we go to these scenarios, we'll see all the intersections. But if you do it in this way, you're not going to get all the intersection points because of that. So I'm looking for the angles such that the sine of those angles are equal to the reference angle that gives you the 1/2, and that reference angle is pi over 6. And then plus 2 pi n, 360 degrees rotations from pi over 6. But there's also other ones, right? So that's just the one positive angle. The other positive angle in between 0 and 2 pi would be at 5 pi over 6. And then divide by 2. Be pi n, but let's make it 12 pi all over 12 n. And then for the other guy, 5 pi over 12, and then 2 pi n over 2, which is pi n, but we're going to, again, rewrite it as 12 pi over 12n just to make the calculation easier. So I need to find all angles in between 0 and 2 pi. So I start when n equals 0. I get theta equals pi over 12 plus 0. And then when n equals 1, I'll get 13 pi over 12. And then when n equals 2, I'll get too much, right? It'll be 25 pi over 12, so I don't get any more. No more help. Okay, and the other guy, starting at n equals 0 again, I get theta equals 5 pi over 12. And then 5 pi over 12 plus 12 pi over 12, 17 pi over 12. But then if you go another pi, it'll jump out of that range. So, the point is we're supposed to get 8 answers. We only get 4. And it's because the r equals 2 formula is never going to be equal to -2, whereas when we graphed the rose petal, in order to get some of those points, we were on the negative side of the sector, right? So when you set them equal to each other, you're not going to pick up those locations. What's the remedy for this? Well, use the pictures first off, and then you could think in terms of symmetry if somebody was mean enough to ask you for all 8 points, which I'm not that kind of teacher. I wouldn't do that. So anyways, there are our intersection points, and it seems the smallest possible one is the one we need. It's the pi over 12. Okay. So this angle alpha is pi over 12. So we're going to integrate from 0 to pi over 12, and the curve we use there is the rose curve, and then we're going to integrate from pi over 12 to pi over 4, and the curve we use there is going to be the r equals 2 curve. That will be the bottom curve. And then we're just going to multiply it by 8. Okay, so at the end of the day, it'll be, all right, so the first curve, we use the rose curve. And in that integral, we're going from 0 to pi over 12. And then adding in the circle curve, so r equals 2, and then we square it. And for that, we're going from pi over 12 to pi over 4. And that just gives me 1/8 of what I need. So what I do then is multiply all that by 8. Right? Let's just cut the video there. I'm sure you can integrate that. These videos are long enough. Okay. All right. So arc length then is the last thing. And we've had 2 arc length formulas so far. So arc length from A to B is the square root of 1 plus f prime of x squared dx. The parametric form, now in terms of t though, so maybe we should change it from A to B, but I'm too lazy. It'll be x prime of t squared plus y prime of t squared dt. And of course you could then put in the formulas, the conversion formula. So x prime of t is going to be that nasty thing that you would get if you plugged it in, r cosine theta basically, where r is f of theta. So it'd be f of theta cosine theta, its derivative, plug it in there. But at the end of the day, what you get is just going to be the integral of f of theta squared, where f of theta is your r formula, and then plus f prime of theta squared, believe it or not. At the end of the day, though, it's really only these 2 formulas you're going to need to know for Calc 3. You wouldn't need that polar form, because the polar equations you can always think of as kind of like parametric equations, and they can just use parametric formulas. Okay, but anyways, let's look at what they have in WebAssign. First, I'll get my derivative. Oh, I want to go from pi over 6 to negative pi over 6 to pi over 6. And so our prime is going to be negative 3a sine theta. And then, here we go. So it's just plug and chug, right? So negative pi over 6 to pi over 6, square root of, and like I was saying, these things are your f of theta, and this is your f prime of theta. So it's going to be 9a squared cosine squared theta plus 9a squared sine squared theta d theta. And then you could simplify that, factor out the 9a squared. And of course, cosine squared plus sine squared is going to be equal to 1. So that'll just be the integral of the square root of 9a squared. The square root of 9a squared is 3a. The integral of theta is d theta is just theta, so you get 3a theta, negative pi over 6 to pi over 6. And of course that will be 3a times pi over 6 minus negative pi over 6, which will be 3a times 2 pi over 6. 2 pi over 6 is pi over 3. The 3's will cancel and you just get a times pi. Okay? Okay, thank you for watching. See you next time.